In this video, we'll talk about how to make a servo operate a switch or point on your model railway and how to make an Arduino drive the servo. The first thing to do is to get the Arduino to move the servo so that you can see how it moves and how it might fit on your layout. Here I have used the smallest servo I could buy. It runs on 5 volts, so it can be connected directly to the Arduino, and it needs one I/O pin to send it the angle information. I have used a Leo stick from Freetronics, but any Arduino would work. The Leo stick has a buzzer and 3-color LED already on the board, so it is very tinkering friendly. On this test rig there is also a sensor. For the sensor I have used a device which is conveniently packaged by Adafruit with the 2 resistors you need to set it up. It comes as a reflection sensor, but if you need a transmission sensor it is easy to take the diode and phototransistor out of the case and mount them apart. When building on the Arduino, I always use a prototyping board with an extra set of long pins on it to make it easy to solder wires onto the board when setting things up. The connections are as shown in the diagram. If you're already doing railway modeling, you'll have no trouble soldering this up. When it's ready to test, it will look something like this. Now to the Arduino sketch. The code here is not the minimum required, but it has the facilities already built in, so that hopefully it's a good base which you can modify to suit your needs and layout. Here I will talk about only the specific things required to drive the servo from the sensor. They are highlighted in yellow. The rest of the code is error checking and other homework. The code here is set up so that it has all the things you need to build and expand to a moderately complex layout. First, set the constants for the pins used for the servo and the sensor. Always define these as constants so that if you change the pins later it's easy to update the code. I always define every pin, even the ones I'm not using, so that I can easily pick the next one and I don't double up. Also define constant numbers which are used for labels and other indicators, in this case the direction names for the point or switch. To use the servo, you need to load the servo library. It is already installed in the Arduino software, so there's nothing you need to do beyond this line. The angle information is sent to the servo as a pulse width. A 1 millisecond pulse sets the arm at 0 degrees, and a 2 millisecond pulse sets it at 180 degrees. The logic to do this is in the servo library. We just tell it the angle we want to use, and it sends the right pulse to the servo. You'll see the code that does this in a few seconds. You need to define each servo you're going to use and tell the library which pin the servo is connected to. For other I/O pins, you need to tell the Arduino whether they are an input or an output, so here declare the sensor pin to be an input. Here is the code which actually moves the servo. The command to the servo is the angle to which you wish the horn arm to move. So you need to set the sweep value to be the right value for your layout. Here is the important code which actually sets the servo angle. If the direction requested is south, then set angle south. If the direction requested is north, set angle north. If the direction requested was something else, then record an error. This error should never occur, of course, but it is very helpful to check for every possible error and even a few impossible ones. This will save you a lot of time in the long run because it also helps you find spelling errors and other problems as well as the obvious error of logic. Errors of the programmer in writing the instructions are much more common than errors of the computer in carrying them out. The function doWriteLog writes messages to the serial port. This is very useful for understanding what's going on, and you can turn this feature on and off as required. The function triggerSensor checks the sensor pin and returns true if the pin is low, which is what you want for this type of sensor. The function triggerWaitTimeout returns true if the program has been in the same state for more than the period param_state_wait, which here is set for about 3 seconds. Note that here we don't use the Arduino delay function at all. We record when we started, then each time round the loop we check to see if we're done. The function getDwell returns the number of seconds in the current state. These functions are where the logic jumps between states. As you can see, to jump into state siding, we set the 3-color LED to show red, then we set the point or switch to direction south, then we beep. The function setState just stores what state we're in, and getState returns the state value. So here's the main logic. If in state wait, if the sensor is not triggered, do nothing. If the sensor is triggered, jump to state siding, setting the rail switch as you go. If in state siding, wait till we have been in this state for 3 seconds, then jump to state main, setting the rail switch back to main as we go. If in state main, wait until we have been here for 3 seconds, and if the sensor is not triggered, then move to state wait. If you've had a problem, do flash LED will flash the LED white to indicate the fault code so that your human can fix the mistake they made when programming you. The rest of the code is doing housekeeping tasks such as recording faults and sending text to the serial port. So back to the real world. Here we have the code loaded on a Leo stick and the sensor and servo fitted. As you can see, when it starts up, it beeps and the LED changes colour, red, green and blue. Here the servo is set to sweep through its full angle movement and uses only a timer. Here it is set to sweep through a smaller angle and is triggered by the sensor. If you trigger the sensor, the servo will move, then after a period return. This is the motion required to move a rail switch or point. Notice also what happens if the object is at an angle to the sensor. The sensor relies on light being reflected back to the detector, so if the light is reflected away in another direction, in this case up towards the camera, the detector won't detect anything. It's necessary to ensure that whatever the detector should see reflects the light back into the detector. To connect the servo to a rail switch, you need a stiff, springy wire which you can bend. Use the largest wire which will fit through the hole in your rail point and through the hole in the servo horn. I used 32 thou piano wire. Make a zigzag bend in the wire at the servo end, just where the wire hooks into the servo arm. This allows easy micro adjustment of the wire length and also prevents the servo from damaging the point while being set up. Where the wire goes through the servo horn, don't bend this over so that it is secured in the servo horn. Use your layout to hold it in place. The reason for this is that if the servo moves unexpectedly, you want the wire to jump out without damaging the track components or the servo mounting.